Okay, so today we're going to talk about ships' propellers. Now, propellers might look like pretty simple pieces of equipment, but there's actually a lot of mathematics and physics that goes into their design. The purpose of any propeller is to convert rotational mechanical energy into kinetic energy on the ship's hull in the form of thrust, and they do generate a lot of thrust. The largest container ship propellers will be more than 10 meters in diameter and can weigh more than 100 tons. Now, propellers are designed very, very carefully to be economical at a particular operating speed. See, most ships, commercial ships, most of their life, they'll be operating at a given speed. You know, a tanker might be something like 12 knots. So the propeller will be carefully designed to be at its most efficient to create the best ratio of thrust from fuel used at that exact speed. And its efficiency will reduce if we go above or below that speed. So propellers are traditionally made mostly from copper alloy, aluminium, nickel, bronze, and some stainless steel. And the reason that these materials are chosen is that they give the best ratio of strength to mass, to cost, to also the melting point of the metals for the purposes of forging. Propellers are very, very finely machined, exacting to millimeters of tolerance on an object of 100 tons, because even very minor imperfections going round and round and round 100 times a minute for a lifetime can create serious inefficiencies, reduced thrust, increased hydrodynamic drag, vibration, noise, and all sorts of things that we don't want. Now, one of the most important things for any deck officer to understand is probably proper propeller immersion. So this is particularly important when the vessel is at a lower than average draft, if you're in ballast, or if the vessel's in heavy weather, pitching or heaving significantly. Propeller down aft can come out of the water, and once it breaches that waterline, you're going to have reduced thrust, you're going to have less effective steering, and you can also put tremendous force on the prop shaft and the engine that it's connected to. Cavitation on a propeller is caused by millions and millions of microscopic bubbles forming at the leading edge of the bite of the propeller, and then those bubbles collapsing onto the blade or the trailing edge of the propeller. Now, these bubbles form because the water ahead of the leading edge of the propeller is actually boiling. Okay, so let me explain. When the propeller is turning, it's sucking water from ahead of the propeller and thrusting it aft. Therefore, there's a high pressure zone abaft the propeller, but ahead of the propeller, there's a low pressure zone. Now, if we remember back to high school science class, when you reduce the pressure of any fluid, you also correspondingly reduce its boiling point. And it's actually possible to reduce its boiling point so far that it boils at its ambient temperature. And that's what's happening here. This low pressure zone sucking the water towards the propeller reduces the pressure, which reduces the boiling point down to, let's say, 20 degrees Celsius, which is actually the ambient temperature of the ocean. So tiny steam bubbles, vapor bubbles, start to form in the water as it boils. As these vapor bubbles get to the propeller, that pressure zone suddenly changes and the vapor bubbles implode in on themselves. And when they do that, they actually do it with great force, and a supersonic shockwave crushes through these little tiny bubbles and impacts onto the propeller blade. When it does that, one study found that the force exerted is about 7 kilograms per square centimeter. Now, that's about the same force as a hammer blow. It's tremendously damaging to the propeller, and it's something every deck officer needs to be aware of. So cavitation will usually occur where the low pressure zone ahead of the propeller becomes extreme. And this is most common when there's quite a big mismatch between the speed of the ship's hull through the water and the propeller's RPM. So imagine this scenario: you're stopped stationary in the water, and all of a sudden, instantaneously, we ring on 20 knots from the propeller. The ship's hull is not moving through the water, but the propeller is now churning very, very hard. This puts an extreme low pressure zone ahead of the prop. That prop reduces the pressure of the water. The boiling point reduces until it gets to the ambient temperature of the water, and the water ahead of the propeller starts to boil. That's cavitation. And the effect is going to be a little bit like a car spinning its wheels on gravel. It's just not going to be very effective at generating thrust. So remember, if at all possible, use gentle incremental increases in RPM until the propeller speed is loosely matched to the actual hull speed through the water. But of course, never do this at the expense of vessel safety. I'm Cameron. I'm an ex-seafarer, now a maritime lawyer practicing in Dubai, and I mostly just like talking about ships. Follow for more.